Okay, so while Chirag is preparing, I'm going to give a introduction of Chirag. So Chirag is a principal engineer at Qualcomm AI Research, and he's the lead of AIMET, AI model optimization AI model efficiency toolkit. He's responsible for bringing neural network models efficiency to practice by developing the best-in-class tools and platforms for model optimization. And he leads the interdisciplinary and engineering teams driving the vision, roadmap, and customer engagement for the AIMET across various business units. Under his leadership, AIMET and AIMET Model Zoo have played significant role in enabling fixed point energy efficient inference for edge AI cases. And prior to his work in AI, he has extensive experience in wireless communication, leading the design and standardization of various projects including the 3G, 4G small cell technologies and LTE in unlicensed spectrum. All right, so without further introduction, let's welcome Chirag to give us a guest lecture about latest technology. Chirag, it's yours.
Thank you, Professor Songan. Hi, everyone. Thanks for the introduction, Professor. As you know, I'm Chirag Patel. I'm going to talk about AI modelability toolkit. I'm part of Qualcomm AI Research. I'm based in San Diego. Probably most of you have heard about Qualcomm. If not, I think the chips, the modems that are running in your phones largely are provided by Qualcomm. So you should know more about Qualcomm and what I'm going to do. Before talking about AIMET, I will probably give a brief introduction of what AI research we do in Qualcomm itself. And before we starting, right, I wanted to maybe make a quick note on the lecture itself from Professor Songan. I think very interesting course. I have been learning a lot from the course as well. I'm in this area, model optimization, efficient AI inference for a few years now. But every time I watch the lecture series, whenever I get time, I learn something new. So I think thank you, Professor, for putting together this course. Right? It's very helpful for everyone in the industry, and I'm sure for the students and researchers as well. And I look forward to more and more content, and I finish up the lecture series when I get more time. So, okay, so let's get started. I think I don't dwell too much on why we need efficient edge AI inference. And Professor Songan would have taken you through the great challenges for the solution and so forth. From Qualcomm perspective, we are as the mobile first company, and obviously the AI use cases keep on increasing, either on the mobile handsets for smartphones, on automotive use cases, or even cloud and so forth. Right? So everywhere you see AI is there, and we need to make sure that people can develop, deploy models, and develop new use cases and run them more and more efficiently. Right? Like you don't want your battery to drain out when you are running some cool app in the middle, right? So that is really the challenge and premise. I mean, the requirements are many. The model size keep increasing, right? People want faster and faster inference. How do you meet all these constraints, like all these requirements in like edge devices, tiny devices, in line with the theme of the course, TinyML? How do you achieve that really? Right? That is one of the very big area of focus for us at Qualcomm AI Research. And if you take a step back, right, just to give you like a picture view of what we do in the AI research itself. Like broadly, we have three big buckets, like fundamental research, platform research, and applied research. The fundamental research, like it's a bit more longer term research, maybe 3 years, 5 years down the road, or even beyond. Like you can think of generative models, GCNNs, all those technologies, right? Like okay, how do you make use of it? How do you develop those? So we have a core research teams working on that. Then a lot of our other focus is on platform research, where I'll talk more about it. All the things Professor Songan talked about in terms of quantization, compression, neural network research, all those techniques, tools, falls under the platform research, and it's kind of wide gamut. And then all the research outcome from the fundamental research and the platform research makes its way into applied research. Oh, we need to develop motion sensing products or ADAS products for automotive driving, and all the other use cases you can think of. Right? That forms applied research. I'll show you some demos at the end of the lecture where you will see okay, how we are using the platform research, applied research, the fundamental research coming together and to build a more and more compelling use cases and improve user experience overall. And I think the other motivation behind showing this slide, I want to encourage everyone to, okay, when you graduate, take a look at Qualcomm. We always look out for great talent, and you will find something or the other of interest to you, and more importantly, not just interest, but you'll have an opportunity to make a big impact, really, right? Like if you think Google and find how many chipsets we ship out yearly, that's just mind-boggling, right? Billions, it's in billions. You will have an opportunity to make a big impact, right? So definitely give a shout out. Keep us in mind when you're out there looking for opportunities. So just quick snapshot. I'm not going to read through the whole slide here. Out of all the research areas I mentioned, we have developed core technologies where Qualcomm is a leader. Like these are AI first, if you want to think of it that way. For model foundation, compression, we have the state-of-the-art industry-leading toolkit, the AIMET, which I talked about. We demonstrated on-device learning for the first time, right? Like all these things are very challenging when you do it and try to deploy it on devices. Like how do you make it happen in real time on a device? It's on-device learning, predictive learning, learning super resolution segmentation at full HD, at real time 130 FPS, 100 FPS, or whatever the requirement be. Right? Outside the core areas like vision and so forth, Qualcomm roots are in wireless. We are bringing like AI into new fields like wireless, right? So we have a lot of cool stuff there, including 5G and then going beyond 6G and so forth. So again, this is to highlight a lot of the cool innovations that we make at Qualcomm, right? Now let's go bit more deeper into like the areas of interest for the lecture today, like model efficiency. So on the model efficiency front, it's model efficiency. What we need to do. People typically will develop models, train their models in floating point line on GPU, right? Okay, that great. GPUs have a lot of horsepower. How do you deploy this model? Whether they are small, large, does not matter. You need to deploy them on the device from a small IoT device to smartphone or even edge like the devices. You need to make sure that you can maintain thermal or battery life, all those constraints. Right? So to address that, we take a holistic view, focusing on quantization, conditional compute, neural resistance, compiler optimization. Right? So from the underlying technology, the quantization to all the way software optimization that is needed as part of the compiler process, and how do you design the networks itself to begin with better through NAS. So this kind of whole gamut here. And I'm going to talk about a small piece of it, like the quantization part, and feel free to reach out and say that interest for other topics as well later on. So on the quantization front, like Qualcomm has been leading the industry in terms of driving integer. By integer, we mean fixed point inference, integer 8 inference largely. As I mentioned earlier, a lot of training is on SP32, maybe SP16. But really, for efficient, energy efficient inference, our view, and I think we have shown a lot of results, is to do integer inference. That's where our research shines. You can see here, like our research is highlighted in top conferences, and then they did data-free quantization, set the benchmark for integer rate, post-training quantization when it was made available, then came the header round and so forth. And we keep on continuing the research. Just recently, the new read a paper on SP8 and Int8, the pros and cons, what works, what does not work, right? And we take a very holistic view, not just showing the results, but okay, what are the system implications for that? And all this research comes out and makes it ways into AIMET. And we also have an accompanying AIMET model domain. I'll talk about it in a bit. So what exactly is AIMET? So AIMET is a library of a toolkit containing state-of-the-art quantization and compression techniques. The whole idea is using AIMET is to make models small. So you can go from FP32 to integer 8 or even integer 4. We reduce the model size, not just the model weight size, right? When you try to context, we say, okay, you context the weights, you context the intermediate activation, the intermediate computations, all those things. Even like you say, energy benefits through memory movement, reduction, and so forth. Right? And it's a straightforward process. Like, oh, you have take models trained in PyTorch and Ceplo. We recently added Keras support as well. You take those models, optimize through AIMET, take those optimized models, deploy on target, and then yeah, it could be whatever targets you care for. Whether so we support Snapdragon devices, right? Like Snapdragon processor from Qualcomm is available, the chipset, card, and so forth. So you can take those models end to end and the best performance. So to give you a quick overview of the features and itself, like we have three broad categories of features: so condensation, compression, and the other is the visualization analysis tools, more of utilities to aid condensation compression. So on the condensation front, we have state-of-art intake for techniques. And here, if you see broadly, I think Professor Sangani, one of the experiments, or portion condensation over treatment. So broadly on the technique in the same. But for underneath, for example, for portioning condensation, your data free condensation, adaptive rounding. We also do automatic distillation. Multiple is available on like Int8, Int16, Int16. How do you make best use automatic distillation? So we have those kind of techniques as well. And then, okay, from the end user perspective, all these techniques are good, but okay, I want a simple workflow. How do I get it at them? So where Autopart is coming, which put together the different portioning condensation techniques and apply them correctly in the right manner to get the best possible answer. A lot of times, portioning condensation may not be enough, especially if you have very challenging models. That's where we have condensation about training. You must have heard about QAT in the refresher as well. I think largely based on the certain foundational principles. But then what we AIMET does is like, oh, it allows you to optimize for a given target by configuring things properly in the sense where do you put the condition nodes and to get the best performance, right? You can do layer fusion, all those things depending on the target requirements or what the target the runtime will do. Outside of compression, we have compression techniques. Largely in like we have tensor decomposition techniques, what we call singular value or special singular value decomposition based technique. And pruning, I think your professor Songan was talking about pruning. We support channel pruning, and then our research has shown that for the best performance, you really need to combine the two, like SVD and channel pruning together, and then you can eke out more gains when you're trying to compress the models. And on this, as I mentioned, visualization tools to okay. If you want to, given a model, you want to understand, okay, what is my distribution looking like for weights or intermediate output or activations, which layers are more sensitive to quantization, or they're more amenable to compression. All those insights you can draw through some of the visualization we offer, right? And I forgot to mention, AIMET is available in open source, so I'll show you like the GitHub page, some example as well, so that you can go and try it out and you get first-hand experience, right? And all these features clearly bring significant benefits. Like, okay, when you contact, you get lower power, lower memory bandwidth, get access to energy efficiency. But the key point here is that when you do context compression, you want to maintain the model accuracy. Right? So that is where AIMET really comes in. It's optimizing the model, but without sacrificing the accuracy or the KPI required, a floating point model. And this is very crucial when you're actually dealing with a lot of critical applications or when because customers will want, oh, they have put a lot of effort training their model and floating point. Okay, some accuracy drop is started, but not too much. That is what AIMET will try to ensure using all these techniques. So I'm going to give some example results and like yeah, and what I would encourage you can search some of these papers that are available on archive as well if you want to dive deeper into the underlying research itself. So the first one I'm going to highlight is like for adaptive rounding. Typically, like let's say you had 8-bit quantization, right? The grid will be uniform grid -127 to 128. And generally, what everyone will do, okay, if the floating point value was here, you do rounding to nearest. Right? There's literature out there saying stochastic rounding is better and or works better in a lot of the cases, right? Not always. So can you do something better than stochastic rounding and uniform the rounding to nearest? Right? And the answer is yes, and that is right? Given this point, the add-on asks the question of whether to round this particular weight value in a tensor to the nearest grid or the next adjacent grid. Right? And it does this optimization. Again, it's a post-training condition. So you don't need to do fine-tuning of the model itself. You feed in some the representative calibration data set, maybe 500,000 images. You can feed that into and optimize your model using adaptive or add-on. And underneath what it does is really like there's a layer by layer optimization of the weights using like a cost function and linear. Think of a MSC based optimization where we decide with some regularization where the decision is okay, how should I nudge the weight so that it rounds off to the nearest or one of the height value, the grid point. And so to see the benefits here, right? Like for example, there's an object detection real use case for an ADAS network. I'll show some images also. So this was like if you see the floating point model performance is 82.2. If you just did nearest rounding quantization with 8-bit weights, 8-bit activation, there's a significant drop in MIP. Right? But with the around you can actually recover it. Right? So the performance is almost close to floating point. It's like more in the acceptable territory. Right? And we have shown that the add-on can also be used for 40 bits. Here you can see the example for deep lab V3. The performance here is very close to or comparable to 14.9. And then there are other techniques you have done to improve further as well. But add-around is one of the key or marquee techniques in post-training quantization. Works across a lot of use cases that we have looked at. And then just to give a bit more color to it, like for example, the first say the object detection model I was talking about earlier, right? Like if you did nearest to rounding in the baseline, you can see this vehicle's bounding box is missing, right? Even some of the classes are incorrect. While with add around, you can get very good performance, right? No missing boxes, each vehicle is correctly identified and so forth. All this become very critical for ADAS applications. So add-on helps on this one. So just I mentioned Autopart. So what Autopart does is it automates like the post-training quantization workflow. So we have different techniques as I mentioned earlier, like cross-layer equalization, adaptive rounding, or automatic mixed precision. So Autopart, you don't have to worry about what should I use, how should I use it. You can directly go and bring in your model. You can call the Autopart APIs, and then in the out you will get a model which will be optimized as best as possible, right? Like not saying that post-train quantization is like cure all. Some models you will need to do quantization over train, but yeah, what autocont will do, it will give you the best possible answer within the post-training constraint. Right? So it's a very simple interface API, easy to use. So for a lot of you, maybe some of you work on like the new algorithms or new techniques for quantization, but some of you are focusing more on more use cases, or you develop some new cool algorithm for super resolution or something else. You want to try it out on device. What is it working? How is it working? That's where all this features come into play, right? Like it makes your life easier as an end user who doesn't want to really worry about the nitty-gritties underneath. So we have quantization aware training as well, and again, I won't go necessarily into all the details there. The main point being, like for example, if you're given a network, right, like convolution, ReLU, and so forth, the QAT will put the right placement of nodes, and we do this for the order around and post quantization as well. And then, as part of QAT, we'll fine tune the weights to make them more robust to quantization noise, really, right? And as per, we also have techniques where not alone just the weights, but even the quantization parameters get fine-tuned or learned as part of the fine-tuning process. So it's like you can learn everything under the hood, and at the end you can get really good performance. Like with QAT, we have shown even for challenge networks, the performance is like within 0.5, 0.1 or 1% of SP32 performance. So yeah, just to highlight some of the proof points really, and more about the AIMET models who I was talking about that. So I think after this I'll show you some of the our web page or the GitHub, there's some example and so forth. But AIMET models really is a collection or a repository of pre-trained, ready-to-use quantized models. Like we have some TensorFlow models, we have PyTorch models. Today we have roughly what 30, 35 models now. Just yesterday or day before we released your transformer models. The infer models are also there available. So here I'm just showing results for intake. We have older slide here. But the point is like across a lot of use cases, right? Like classification, pole estimation, super resolution, and so forth, right? Like when you use AML techniques, you can quantize models from SP32 integer, right? And then the accuracy is pretty good. Like largely we see less than 1, the gap between SP32 and integer is 1% or lower, right? So you can even go, I encourage you to go to the website and then check it out. Right? If you want to directly use for some of these models for as a backbones, you can use that as well, right? And then fine tune on your end-to-end use cases for any data set itself. So we're talking about transformer quantization. So yeah, transformer everywhere. There's a new concepts. NLP clearly they have made a lot of breakthroughs, right? Enabled a lot of breakthroughs. So and then transformer quantization is generally considered challenging in literature. And we have shown and the AIMET can actually get quantized transformers as well. Like here you can see bird, district bird, mobile bird, all sorts of models really, right? Then quantized into integer rate with pretty good performance. And you're not just NLP models, you have billion transformers, we are able to quantize them. Even for challenging or critically like a bit more intensive use cases like depth estimation also, performance can be very good. So again, the point being, okay, quantization is possible. AIMET is the tool you should use to quantize data, right? And even the difficult or most difficult challenging models. And we continue to push the envelope more and more, right? So we talked about intake a lot of the time. A lot of industry hardware today is intake. Right? But Qualcomm recently announced as part of Snapdragon Gen 2. Just last month we announced availability of Int4, but Int4 here we mean 4-bit weights, and then all the outputs and intermediate activations can be 8-bit. So just recently that will set the new benchmark going forward for the industry, right? Like in terms of power efficiency you get either from SP32 or from compared to intake, it is significantly much more efficient. And again, here you can see like several use cases, classification, segmentation, supervision, fault detection, and so forth. Even transformer models, we have some results where you can show that okay, 4-bit weights are possible for the whole network. Right? I'm going to show at the end, so we can skip some of this as well. So yeah, that was a quick, very high-level overview of okay, to motivate quantization is possible, and you should give a you try using AIMET for quantization games. And let me then quickly walk you through the GitHub as well. So this is our GitHub page. You can go to github.com/quick/AIMET, and then you will see some resources, tutorials, installation guides, and whatnot. And if you happen to run into issues, reach out to the issues forum here, and we'll actually support on the problems. But let me show you an example, right? And how easy to use it. Again, a lot of times when trying to tool, we worry that okay, how does it work and whatnot, right? So we have ready-made examples, Jupyter notebooks available for different techniques, autofont, context aware training with range learning. So we have all those things available for you to use, right? So if you see, just go to autofont notebook. So yeah, the whole flow workflow is nicely laid out here for you. So yeah, there's an example model and a pipeline, but largely what you need to do is replicate this for your own evaluation and training pipeline, right? So yeah, you have your own training pipeline. You can load a 32 SP32 model, prepare the model. So we have some utilities that allow you, okay, you have a part-out model. It needs to be made AIMET compatible. So because AIMET needs to insert quantization nodes in the graph. So AIMET takes care of it automatically, and that's where the prepare model, validate model utilities come into picture. You use them. Essentially, this is a model ingestion process into AIMET. You can come to the SP32 baseline accuracy or score. Oh, my top one accuracy is this, so on and so forth. Right? Then you bring in like unlabeled data set. I mean, for this all post-training quantization, we don't really need like a training data set for quantization itself. We need validation data set for your validation exports, and then some calibration data set, again unlabeled really. So for the optimization purpose itself. So you will bring that you are using your own data loaders. But none of this requires you to change your training in evaluation pattern. Minor changes will be needed, like what you pass in, pass out, and so forth. But really, you don't need to rewrite your code for the data set and so forth. Right? So, and then just the Autopart itself is a straightforward API. Call the Autopart, and then that's it really. Right? You can set some parameters. So you have some more guidance, documentation on how to set the parameters and so forth. Right? But really, that's about it, right? Like this is real gets you the functioning foundation going, right? So if you have models where you want to try out how can I get it from SP30 to EK, there is the one way. Yeah, and you say, okay, this was like setting up the autocon itself. You run the autocon, and then finally, yeah, you can get the accuracy and then all this thing, right? And then what happens at the output level, like you get a model, it is optimized, you can export it to on it, and so forth. Together with that, you can even you get like condition parameters. Okay, for this weight tensor, these are the condition parameters I need to do, like the scale and offset values or the min max values for the range setting for the condition. So you get all that in a separate file, and then you can use the model optimized model and this file and take it to that target, right? And then on all the Qualcomm devices, we have the interface also available to ingest the model and the JSON file to so that you can deploy it on the target hardware and well get the accuracy. So yeah, which I think there are other examples as well. Right? Like, for example, yeah, cross-layer equalization, foundation aware training. Maybe if I want to quickly show the foundation aware training here, right? Again, foundation aware training, while yeah, it needs some fine-tuning, hyperparameter optimization, good. But largely the workflow is no different than what you will do for your training. Right? The only at the same time, you are not training from scratch, right? That's why it's fine-tuning really. You run some certain number of epochs, 10, 20, 30 epochs, and you are able to fine-tune the network. So again, largely the workflow is same. You bring your evaluation training pipelines, load the model, prepare the model. Like yeah, I think this is like get constant model is really what it prepares the condition simulation model. Uh, and then you perform QAT, right? Like yeah, again, the original pipeline you had, you continue to use that same original training pipeline, and you are able to fine tune the model, right? So the point being, okay, the API is very clean and easy to use. So yeah, you should not be overwhelmed by using AIMET and other underlying techniques within AIMET. Right? So let's quickly go to the model itself, so I can show. Okay, on the models you said, okay, you can see here, right? Like we have PyTorch models, TensorFlow models. You can go to again same github.com/quick/AIMET model. And you can see all sorts of models here, right? Like yeah, mobile net to deep lab to anything I mentioned, right? Like we just recently released transformer models as well, mobile ready, digital bird, mobile bird, and so forth. So all those are also available. And you can see here, right? Like performance, the SP32 result, W88, like the intake model result, and then wherever we have 4-bit models available, we even publish the 4-bit numbers here, right? And those models and checkpoints are available for you to use here. If you go here, we should be able to access the model that gives you this performance level, right? And same thing here. And yeah, so similarly, we have models for TensorFlow as well. Yeah, I think PyTorch is more expensive, but feel free to now it encourage you to use it for your application, or if you're building a cool, fun project in a class, you want to use one of these networks. Yeah, this is the place where you want to start with, right? So, yes, so let me go back to the slide and then we also have a white paper on quantization, right? Like there are two white papers, one is on quantization, like more practices, best practices, and then like a practical guide to quantization using AIMET itself. Right? It's also available on the archive and search for it. That will give you a good exposition to okay. I think Professor Songan has done a fantastic job, like bringing up or making you aware of quantization under what are what is the landscape looking like. So this is a more nutshell summary of that, and then how do you take all those learnings, use it through AIMET. So it will give you a walkthrough of that itself. So yeah, we can then I will talk more about like we talk about one particular aspect of model optimization, which is through AIMET. AIMET is an offline optimization tool. You are not necessarily tied to your target device there, right? As Qualcomm, we offer a full Qualcomm AI stack itself. Like you might have heard of Qualcomm Snapdragon, or recently we recastioned it to Qualcomm AI Engine Direct QNN. So this available when you optimize your models and deploy it on target. This is what actually comes into play. You deploy models using QNN or AI Direct Engine. It's very versatile. It's been there forever now. Support all sort of frameworks, runtimes, right? And yeah, you don't need to worry about the underlying. Uh, yeah, some again, it's a simple API calls to be able to run and deploy your model. But at the same time, what I want to highlight is like, okay, underneath a lot of research that goes into compilers, the accelerators, and so forth on the hardware side, software side. So all that research, a lot of it is in-house. We try to yeah, improve the state of the art on all the fronts, right? So just to give an idea of the practical application and also like what kind of research goes underneath. So I take again, and then to complement the runtime stack is where all the other tools come into play. AIMET also I talked about. Your architecture search is something we have available, and then also in-house work as well. Because Songar also talked about new NAS and so forth, right? Want to quickly also highlight like the Qualcomm Snapdragon 8 Gen 2. I mentioned it was announced here. So taking a very broad view here, right? Like in the AI engine, Snapdragon chipset, yeah, it's largely an accelerator like ML workloads with realize like tensor processing, metrics or multiplications and so forth. So and that is really the heart and the brain, if you want to call it both, of the Snapdragon for all the AI use cases. And then the recent announcement of highlights are really of reinforced support. What we are doing through AIMET is enabling the reinforced support across a wide range of use cases. And AI engine itself is like significantly improved compared to previous generations, like 60% more power efficient. We also have a sensing hub available, like a lot of users will want, okay, AI workloads are good, but then I need to sense the different modalities, audio, video, vision, whatever you want to make. All I need to sense the surroundings around me, fit into neural network models for use case and care for, right? So you have sensing hub available. You can, yeah. And then I think this is something you will hear more going forward from Song and perhaps and others. We recently and Qualcomm developer kit. So it's essentially a kit with a hardware we offer, like hardware SDK, and together with like the software components like a QNN and others. Right? It will also leverage AIMET, and the intent is to encourage researchers, students to use the Qualcomm platform, build more application on it, how make best use of AI capabilities that are available, showcase right what you can do on top of it. Really. So that is the intent behind the Qualcomm innovator developer kit. I believe there will be some more follow-ups in January on this front. and Professor Songan can guide you more on that. Right? So I think this is my last slide, but what I'm going to do, I'm going to show you some demo videos. And then I want to keep more time on Q&A, and then we can actually go back to the slide, right, for more discussion or what questions students may have or others may have, right? I want to give more time for that. So I want to highlight some of the demos we did recently at UX 2022, and the intent is to show you again the full span of research we do, the full stack research, and to encourage maybe that triggers your mind toward, oh, these are new areas we should focus on or you want to work on it. I want to encourage you on that. So again, all these videos are also available publicly, right? So you can take a look at that. So before I start the video, right, I'm going to show 3-4 demos and then more going to Q&A. So this is more about conditional compute for on-device video understanding. So I think the video will speak for itself, but just to set the stage, videos are like very challenging for processing, especially real time. The resolution keep on increasing, and single frame by frame processing is not the most efficient, right? So can we do something better? That's what this is going to talk about.
Frames. Welcome to the on-device video understanding demo presented by Qualcomm AI Research, where we use conditional computing to process video frames faster and more efficiently. Action recognition from video is useful in many industries such as media, security, and health. Video streams, however, contain many redundancies. In other words, repeated information that is not necessary to process to achieve the same results. Convolutional neural networks designed for action recognition process sequences frame by frame, layer by layer. This leads to accurate results but is extremely compute intensive and leads to high latency as well. We introduced the frame exit model, which automatically learns to process fewer frames for simpler videos and more frames for complex ones. Our model sequentially observes sampled frames from a video up to a current time step. Then it uses a gating module to automatically determine the earliest exiting point in processing where an inference is sufficiently reliable. To enable execution of the model on device, we use state-of-the-art quantization techniques from the open-sourced AI Model Efficiency Toolkit, AIMET, and a novel compiler stack that supports models with dynamic inference graphs. Now let's see the demo in action. We apply inference on videos at playback on 2 separate Snapdragon-powered smartphones, one for frame exit and one for the baseline. Frame exit on the bottom can classify the action early and exit, while the baseline model on the top must see the full video to reach the same accuracy. Our model outperforms competing methods on commonly used action recognition benchmarks and enables a 5 times reduction in compute and latency at comparable accuracy on average. Stay tuned for more advances in conditional compute.
Yeah, so see here, two things I want to highlight is one is obviously quantization was needed, AIMET was needed to deploy and run the model on device. Right? But outside of that, what we did was to get full system view. Okay, you need to do some compiler optimization, enable new compiler functionalities for this conditional compute kind of work. So we enabled that. And then obviously the quantization piece. And then before that, actually, okay, how do you do conditional compute itself, right? The gating mechanism, the idea is very intuitive. Like, oh, the only where frames are quite complex, the scene level change significantly. You want to process, put your horsepower to those kind of frames, right? If there is not very much change, you can get away with limited processing. So from the actual design of the model techniques to quantization, optimization, and then finally for the on-target compiler optimization or the compiler development itself, right? You can again see the theme of okay, end-to-end research, right? So we don't just focus on one particular aspect or area, and this is what helps us drive a lot of innovation, especially on the hype side. So I talked about Lean 4, right? So real time mean for super resolution. Right? Super resolution is one of the extremely challenging use cases. A lot of folks, customers want to look at pixel by pixel with 100x zoom. Okay, what is my super like inequality looking like? Right? And we have been able to show that even under these circumstances, Infor actually works. So that's this demo.
Welcome to the world's first on-device demo of real-time super resolution using a 4-bit integer model, presented by Qualcomm AI Research. Super resolution clarifies, sharpens, and upscales an image to higher resolution. Applications like gaming and video playback, along with the ever-improved display capabilities of TVs, smartphones, and VR headsets, are driving the need for efficient scaling solutions. AI-based super resolution achieves impressive results in terms of visual quality compared to traditional approaches. However, enabling accurate AI super resolution on mobile devices with compute, thermal, and power constraints is challenging with existing. Mobile gaming, in particular, would benefit from efficient super resolution architectures to address heavy compute workloads such as sustained high frame rates above 60 frames per second and high resolution images up to 4K. To address these challenges, we optimize across a full AI stack, including the algorithm, software, and Snapdragon hardware. We developed a simple yet effective single image super resolution architecture, QSRNet. It provides better accuracy to latency trade-offs than existing neural architectures through optimizations like removing parallel branches, collapsing residual connections, or clipping ReLU activations. We further reduced the model size by quantizing it to 4-bit integer from 32-bit floating point. We use the AI Model Efficiency Toolkit, or AIMET, to apply state-of-the-art post-training and quantization-aware training techniques to maintain the accuracy of the original model. Finally, we deployed the model on a Snapdragon-powered phone utilizing the 4-bit integer hardware acceleration to increase performance, reduce latency, and increase power efficiency. Now let's jump to the 4K super resolution demo running at 100 plus frames per second on a smartphone. Here you can see the side-by-side comparison of the 4 times upscaled super resolved image and its low resolution counterpart. Our super resolution model on the right provides higher accuracy and crisper images. Quantitatively, you can see that our QSRNet model obtains better accuracy to latency trade-offs than existing deep learning-based architectures across model sizes. In fact, our lighter weight versions are 40% faster than existing architectures for the same level of accuracy. Moving to 4-bit integer has a dramatic improvement on not only latency, but also power consumption. In comparison to 8-bit integer, performance and power efficiency improved by 1.5 to 2 times. Besides super resolution, AIMET techniques can be applied to enable int4 quantization.
Yes, so I think this was more about Int4, and you can see real time on the running on super resolution, 4K super resolution running on device. So that's pretty neat actually. And this is the S cutting edge state of the art it can get. And the Snapdragon Gen 2 will be available in smartphones in coming year, right? So this is like the most latest and greatest that we have to show. I have some other demos as well, like 3D reconstruction, especially XR, AR is becoming more and more hot. But I think I'll take the pause and I encourage, sorry for it, attention the links of and check out. And then also on-device learning for basically, right? So a lot of people talk about on-device learning, but there's a demo showing actually how can you teach an AI assistant running on device through few learning. And again, these are multimodal learning, right? So voice, speech plus gesture recognition combined together. And then you have to train an AI agent on the device. So with that, I'm going to pause actually, and then Professor Songa and like, yeah, maybe I don't know how it will work. questions, and then if you want, we can go back to the slides as well. And I want to leave some time for more questions, not just on the presentation, but if you have more broader questions on AI, Qualcomm, other questions, I'll be happy to answer. Right? So.
Okay, sounds good. Thank you, Chirag, for the nice presentation. The technology is truly amazing. The demos are really cool.